Okay, so let me welcome you to the next lecture on peer-to-peer networks and applications. In the beginning of this lecture, again, I'm recording the lecture, and this time I also have some announcement that is relevant for us. So we have a problem, as I was told, and the problem is that the lecture time currently is now, so Tuesdays from 4 to 6, and the lecture is in English, and there's also the German course for the English-speaking students at the same time. So typically, during the making of the schedule, that should not happen, but somehow the organizers managed to put it together. So there's a collision, and we have to reschedule our lecture in order to give the opportunity for the English-speaking students to also visit the German course. And as I see, there's also some people involved in this issue. So we have. So how many of you are really hit by that collision? So how many of you are going to the German class? Okay, that's roughly 10. And we have following slots also in this building at different locations. All are suitable. And out of these 4 slots, we should choose 2, one for the lecture and one for the exercise. So, and what I would like to do now is to go through these 4 slots. Probably you should also try to pick out your weekly schedule of your lectures so that you are aware of when you have some dates, and then we will vote for each of these slots and at which time most of us has some time. Yes. So I would like to, so we have 3 slots on Tuesday. So the one is the current one, which is now used for the exercises from 9 to 11. Then we have a time slot from 11 to 1 and one in the evening. Yeah. And one is on Friday from 11 to 13. So how many of you are for the first slot? So how many of you would have time at Tuesdays from 9 to 11? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, good question. So we have the opportunity to also rescue. So both the lecture and the exercises can be shifted around. So that's not having any effect. So we can, if we decide to put the lecture at this time, we will have to find another time for the exercises. So for example, the exercises, which are 2 weekly, could be then in the evening or could be on Fridays or met from 11 to 13. So what I would like to do now is to first collect when most of us have time, and then to see where the majority has time. That would be probably the lecture. And where the second most people are available, that would be the exercises. Okay, so let's make the vote again for Tuesdays from 9 to 11. Who's available? 2, 4, 5, 6, 7, 8, 9, 10. Okay. Just keep the hands up. It's I have to count them manually. So 5, 7, 9, 10, 15, 20, 23, I think. Okay. So who of you is available Tuesdays from 11 to 1? Please raise your hand now. So, okay, now I count. So that's 5, 6, 7, 8, 9, 10, 16. If I corrected correctly. Okay. Who's available Tuesday evenings from 6 to 8? Please raise your hand now. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, okay. And who's available Fridays from 11 to 1? Please raise your hand. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So we, according to this poll, we would place the lecture. Okay. Yeah, we would place the lecture on Tuesday morning from 9 to 11. I would suggest that the lecture time, so the lecture begins then at 9:15. No?
My next lecture is at 11 at the university.
Okay. Okay, then from 9 to 11, from 9 to 10:30, 10:40. And the exercise will be 2 weekly in the same schedule like now, but at the time 11 to 1. Yeah, I like this. Okay, so this was the last lecture at this time slot. Yes, there are some questions. Yes.
Probably another outcome if we change the lecture from 1 to 3, 5. So we wanted, like the other ones to 2, 4, 6. My lectures, I've got another exercise on that.
Okay. Yes, yeah. Yes.
Exercises are on 1, 3, 5, and 1, 2, 3, 5.
Okay. Yes. We have the option for this. Yes. So we can also make a poll for that. In that case, I would. Yes. I just the 2, 4, and 1, 3. So now we have it in the schedule 1, 3. Now let's do it the other way around. Okay. So who is then for the option for the exercises like we have it now? So to keep it, to start with the first exercise next week. Please raise your hands. Okay, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Okay, that means so that means if you change the order, then we would have had this week an exercise. So the next week will be in the next exercise will be in 2 weeks. That means because we cannot hold the first exercise, I just will put it online so that we still have the 7 exercises in total like we would have had. So who's then for the option to have it in 2nd and 4th week, starting basically from this week and have the next one in 2 weeks? So please raise your hand. 1, 2, 3, 4, 5, 6. Okay. So I see most of you don't want to have exercises, but okay, so we will keep it like now. Yes? Yes, that's true. So all of these options that were got free, so 11 to 1 and Tuesday in the evening, that probably not, but Friday, there are always some collisions. But only collisions with one, as I've heard, dedicated lecture, so not most of you are hit. Okay, so then we have a conclusion. What we will do is to keep the exercises in the same period. The next and first exercise will be next week, and these are the new lecture and exercise times. You have a question? That's true. Yes, as I was said, the problem is that all 3 slots that I was given to choose from have some collisions with other lectures. But these collisions only hit some of you, but not that big majority. So we have to. I can just offer you to look at the recordings then. Sorry. Okay. And yeah, something I wanted to say last time. On the website, you find all the content for this lecture that will come, and you find also the recordings. So just have a look. If you miss some lecture, you can download it and also print out the slides in before. Okay. So let's start then with the lecture like it was intended. This time, so last time we had a long introduction in peer-to-peer networks, and this time we will have a look at one special type of peer-to-peer overlays, and which are namely unstructured peer-to-peer overlays. So we'll have a look at 2 types. So one, the homogeneous type of peer-to-peer overlays, and look into centralized peer-to-peer networks, also that kind exist, and some more overview on homogeneous, what the term especially means, peer-to-peer overlays, and especially in 2 versions. So one is Gnutella version 0.4. That's one prototype which is very often referred to, and one rendezvous-based peer-to-peer overlay. And then we will see. Let's see whether we come today so far. So we'll have a look at heterogeneous peer-to-peer overlays, which basically takes into account the quality and the capacity of the peers, and see how this can be done with distributed servers, with supernodes, and how Skype does it, because they also use some peer capacity estimation. Okay, so let's start with the unstructured homogeneous peer-to-peer overlays. In order to put it somehow in context of the other overlays, so in this lecture, in the first 2, 3, we will have a look. So now we are on the part of unstructured peer-to-peer overlays, and we will have a look how all these other variants come into play. So just to give you a help of what kind of terminology we use, what homogeneous and heterogeneous means, and what structured means, and what else exists, I have an overview of the terminology. So last lecture we learned how basically peer-to-peer overlays, what's the core of them. So you have nodes that are somehow managing resources like files, and the main task is how can I find this corresponding file in the network. So that's the rough idea, and the peers for that create a distributed self-organizing network and have some protocols inside which help you to find documents that you would like to find. And the one type of overlay is termed structured, that we saw last time, and the main point in this is that the objects are not just randomly placed somewhere in the network, but you have really dedicated peers which are responsible for them. So every object has a specific object ID, and you have a peer who's responsible for that object ID. And what that structured P2P overlays can do is to find really the peer responsible for that specific ID. The other type, what we will look in this lecture on, is today at least, is unstructured peer-to-peer overlays. There you don't have that link between objects and peers. The objects don't have special names, so they just they are not linked to special peers. So if you have an object that you want to publish, it just stays on your device. And the question is then, how do I find these files? How do I find the objects I'm looking for? And for that you have search by keyword. There we will learn some mechanisms today. Following the further terminology, so we have pure and hybrid peer-to-peer overlays. Pure means that all nodes in the peer-to-peer overlay are operated by users. They are not special, they are just common devices. In the hybrid version, there we have also some servers inside. So that means that we have some stronger components, we have stronger roles. So that means the main idea is whether I have some server enhanced network or not. That's the difference between pure and hybrid peer-to-peer overlays. Most of them that we will learn are pure. Then we have homogeneity and heterogeneity. Homogeneity is referring to the Greek verb of being equal, and there also the concept is that all the nodes perform the same protocols, so they are all equal in their roles, and they do the same basically. In heterogeneity, there we assume that the nodes have different capacities, and we should also give them, according to their capacity, different roles. So we introduce various roles and try to assign them to the peers according to their properties. For example, again we will see some examples both for homogeneous, that will be the first part of this today's lecture, and some for heterogeneous overlays, that will be the second part. And finally, from the terminology point of view, we have flat overlays. That means if you just think of a typical overlay, all the nodes do the same, you have only one network layer. If you have a hierarchical overlay, there you introduce several overlays which somehow use each other's capabilities. So there you have several network layers if you think of layering. And each layer has a dedicated function. We will also see an example for that. Okay, having seen the broad overview on terminology, now I want to go more deeply in this unstructured peer-to-peer overlays. So the main concept there was that I do not link objects to specific files, to specific peers. So the point is, if you upload or submit a resource, that means a file, you just store it on your own device. And the question is, how do I find it? So every peer is only responsible for the objects it submitted and which it downloaded. So you don't really create a further data structure that tells you where to find some documents. So the main task, because now you have a distributed network, the nodes have some links to each other. The question is, how do I find something I'm looking for? So that also is referring to the term search or keyword search, because you can also define several keywords that you are looking for, or some more complex matches. So coming from the old times of file sharing, when you wanted to download some MP3 file, there you defined, for example, the lead singer and probably the file type and probably the message size, so that you can define some further requirements for that search. And the peer-to-peer overlay gives you then a list of files and a list of peers which are matching to it. Okay, so the very first and very simplest overlay that performs this requirement and this functionality is not really an overlay, but it's still termed under peer-to-peer networks. So the main overlay and the main search functionality is done by a server. That's the simplest way that you can do. So you have a large number of nodes and you have a server, and the server is maintaining an index. An index, that's a term that we will come up a lot of times, many times, and that means it's listing what you can find where. And if you use a server, then it's simple. You just have a list of what, so object name, file name, criteria, ID3 tags, and the corresponding peer which stores it. So IP address and port. And it's very simple to find specific documents that you are looking for. So what you have to do is, if you are a peer, you have your own objects. You somehow have it if looking at the whole peer-to-peer network, you have it decentrally stored with a centralized index, and it's very simple to operate. So I'm not even sure. There's an example how this is working out. So as you can already see, if you have some files, you just tell what you have and you are looking for it, you ask the server. So, and afterwards you know who is storing it, so you can directly contact him and ask him to provide you with the file. issues are, of course, the costs are unbalanced, so the whole load and the whole costs are at the server side, and also the server's single point of failure. So if the server crashes, then everything is lost. So to have it more formally, how does the protocol work? It's basically having only one single server. You tell him what you have, and if you want something, you ask the server for the document and for the requirements, and then you are happy. I think the picture is not quite correct because you shouldn't root over the other nodes. So just ignore that picture. It should be more like this picture. So you just transfer what you have and ask what you want to have, and you get the address of the node that you can ask to download it from. Okay, so advantages. So it's very fast. So you just ask the server. You can have very complex and fuzzy queries because you have all the information, all the index at one position, and it's simple, and fast. And this indexing information, if you just think of some large movie files that you are indexing, it's typically not so much. So corresponding to one big movie file of 700 megabytes, so I don't know what's the current size, so probably a DVD size, 4.7 gigabytes. They only need the name and so the actors' names probably, and the length of the movie, and all taking this together is probably 1 or 2 kilobytes. So that's very small that you need for indexing. However, it still doesn't scale very well. So the server needs to maintain the index of all of these nodes and has to maintain the global view. And it's also a single point of failure or attack. So if the server is down, then your application is worthless. Also the nonlinear increasing implementation and maintenance costs. So if you have a server, then typically it's only usable up to a specific size, so a specific number of users or a specific size of your index. But if you exceed it, then you need further operating computational power or memory, then it's hard to upgrade. Probably with the cloud it's more user-friendly now, but still it was an issue at that time. So, concludingly, if you have a very large network, then you have some problems, because it's hard to operate the server, it's costly. But if it's small and you are not afraid of having some legal issues, then it's still the very good solution. But we want to have still some distributed solutions. So looking at why is it relevant, basically because of Napster. Napster was one of the first really famous peer-to-peer file sharing system. I think it's also said the first at all. And the nice thing it offered in 1999 is that you could really download MP3 files for free, and that was a time when just MP3 was basically discovered and freely usable. But then they had some problems with the media. So they were asking Napster to stop violating copyrights of artists, so they had to introduce some filters, so you were not allowed to look for Britney Spears but for Barney Spears or something, and not for music but for music. Some letter changes could help you at that time, and also that was obvious for the media right owners. So at the end they asked, so they didn't ask, but they forced Napster to shut down and to stop its business. So nowadays there's still Napster with the same logo. Let's call it Napster 2, and it's a music store, not peer-to-peer at all. And you can nowadays stream any kind of music for free, not for free, but with a monthly fee. I think if you pay $10 or so, then you can have access to a very large database of music files. So that was the history to Napster. Still, looking at the exact phases that they used, it's a little bit slightly different than we had it in general concept. So you have the directory update where you just tell everything about your files. You have the search phase, where you ask the central server for peer addresses which offer something that you want. And then you get a list of peers who offer that file. Then you can, the next phase was basically to test the quality. So you asked, the peer asked every node in this list to determine the bandwidth to them. So in advance, you do not know how fast these peers might send you the file. So you send some ping message, and depending on the delay, you know how much bandwidth you have, basically. And finally, you have the direct download from peer-to-peer, so that's why it's still listed under peer-to-peer network. Okay. Some other application beside Napster that was also using this type of centralized peer-to-peer concept was ICQ, and probably still is. So it was the first instant messaging tool. I don't know that, but at least the first prominent instant messaging tool, and widely deployed, and I still have an account, but I'm not sure whether how many people still use it. So, and what they offered later on, so you use the centralized server to maintain the status of the users, to show whether they are online or offline, also to list your friend list. But what they offered, and in order also used in order to save their bandwidth, is that chatting messages were sent directly from one node to another, only in cases when you were behind the net, so you couldn't be accessed from outside because of your net firewall. The server was used as a relay. That's also something that Skype is using nowadays. And what they also did is that they stored messages until user gets online. So if you compare it to Skype, also Skype uses this relaying using other people's PC for net circumvention. But ICQ stored also the offline messages, so while the users were offline, the messages were stored, something that Skype doesn't do. So if you just notice, if two Skype users come online, or if one Skype user is offline and the message is sent and the second one goes offline, and the previously offline one comes online, then the message is not transferred. The messages in Skype are only transferred if both of them are really online. Okay, so that was also a user of centralized peer-to-peer networking. But as we saw, either use it in a small concept, it works quite fine. But if you want to extend it to a large size like Napster, then you really have that single point of failure, where if the one single server fails, then the whole application is ruined. So that was the motivation and the time when this homogeneous, fully decentralized peer-to-peer networks came to play, namely Gnutella 0.4. And the little picture is also showing the main principle. So what they did basically is to eliminate the server and trying to solve it without. Okay, so having, again, before talking about Gnutella 0.4, just some words on distributed and homogeneous peer-to-peer overlays in general. So the term homogeneous, as it was said previously, is pointing to the fact that all the peers are equal. So you don't have distinct and different roles. So only one type of role. And because of that, we have to provide the mechanism in a fully distributed way so that the peers perform the same protocol, and through this collaborative cooperation and self-organizing protocol, the functionality of search is implemented. And of course, all of the peers only have a local view on the network, so they only know their neighbors. So that means a neighbor is their local, is their contact. So they have a list of contacts, IP addresses and ports whom they might contact, and these are their neighbors in the network, and only they can be used to send messages to. The nice thing about it is, if you have that kind of only local view, that you can organically grow. So if a new network comes to a new node comes into the network, it just attaches somewhere builds its neighbor list, creates some new contacts, but it doesn't need more information about the network. So the network can grow in any directions, so to speak, and the topology is always extended. What the good thing is, and most and highest motivation was to create robustness, so to really eliminate every critical element in the topology. And if you have a random graph, basically, then you don't have critical elements, so every node might go offline. And also to have the self-organization, so because you don't have any specific roles, all of them have to provide the same protocol, and they all together have to self-organizingly provide the functionality of search. So that was also, from research point of view, a very interesting topic. How can this be done? And the tasks that were to solve. So if you eliminate the server, what kind of problems you might come up with? So first of all, how do I come to the network? So before I had my central index server, I just had to contact. So now you need some joining strategies. So what has to be done? Basically, you just need to know one peer in the network, so one element where you can attach, and you basically contact that node for further contacts that you might have as your links. So you only need an entry point, and by asking this entry point and its neighbors for further contact links, you create your own neighborhood. Okay, then you need to search somehow. And there are several mechanisms how this can be implemented. So that you can broadcast, that has some drawbacks and benefits. You can have some expanding ring, random walk, and rendezvous. For all of these 4 points, we will have an example. Okay, with that, we also can search for files we are looking for. And finally, how do we deliver the service? So if the file is found that we are looking for, then that's the same old principle. We just establish the connection directly to that peer and download or transfer the file directly. Okay, so what is really the benefits and what are the drawbacks? The benefits are, what they wanted to do is that really every peer is dispensable. So every peer might go offline, and in that pure peer-to-peer network where you really assume that your devices are operated by private persons, then this is also one assumption that you have to take. So every peer should be able to go offline. What they also wanted to do is to balance the cost. So previously the server had all the load, and now the goal is that every node offers a little bit of bandwidth, a little bit of storage space, and you have solved the issue of search. So no peer should be overloaded. And it's self-organizing, so you don't have to really don't need mechanisms from outside to correct the happenings and the protocols in the network. So it's all working out by itself. We will see that the problems will be that it might be slow and expensive, and because it's a search and the documents might be everywhere. So if you have a network of 1 million nodes, if your mechanism is not very, very clever, and even if it's very clever, you have the problem that you don't find the object, even if it's there. So if you have 1 million nodes and the object is only available once, but you asked only 999,000, then you still didn't found it if it's on the wrong peers. Okay, let's see what kind of basic search mechanisms we might have. So the simplest one is the breadth first search. So that's flooding, commonly known to us. That means that we have a TTL. So what's a TTL? That's a time to live, and that means basically a hop limit. So how many times I propagate that query. And if I'm looking for a specific object with specific criteria, so I define my query that's with several keywords that I'm looking for, I send out this query and define a time to live, probably 7. And every node, so let's assume this node is looking for some file, he sends out the query to his neighbor, so basically to all of his neighbors, and it's just one specific, and he forwards the query to all of his neighbors except the node from which he received it. Yeah, the concept of broadcasting could be known to us. And what is further done is that the time to live is decreased with every hop, so that at the end the query is not flooding the whole network, but only a region within this time to live, so within this hop count region. Okay, what else can be done to improve that? One could store some message identifiers, and if the message is somehow traversing and coming back to us again, then we don't resend it. So this is just some improvement. Here I have an example how this might look like. So the red node is the source node, and the yellow one is the destination node who has that specific object. And this is a very nice animation that took quite a lot of time to do. Yes, great. So looking at it again, so that every node just floods the network and propagates the query further. So in this case, we had a hop count of 5, yeah, because we started with 1 and ended in 6, and 43 messages were sent. Of course, if you think of a larger network with more nodes, then you have an exponential growth of your message size. So if you have a time to live of 8 and you have an average neighbor count of 10, then you have 10 to the power of 8 messages somehow roughly that you generate. So quite a lot. Okay. What is the big point? So with this fully distributed approach, of course, you don't have the central system. And yes, there's a question. Yes, you have to know one. So either you get. So the question was, how do you, just for the recording, how do you join the network if you don't know anybody? So you have to know one, either from the website where you list already members of the network, or what has been also typically done, that you maintain a cache of your known contacts from the last time that you were online, and then you had probably 100 nodes, and you go through all them, try to contact them, and if you find one, then you are happy. If not, then you are accessing the website. Okay. So what was the point? Yeah, they all wanted to basically centralize. They found out was very bad, that they didn't want to do because it's vulnerable. So let's do the absolute opposite and do it only fully distributedly, and don't have any global information, only this local neighborhoods and the flooding. Okay, so the point was, in the worst case, that you have to ask as many systems and devices as possible or necessary until your query is successful. And just imagine if your hop count in the beginning, time to live, was 7 or 8, and you contacted 1 million nodes and still didn't find your object. So what do you do? So you had a high traffic load on network. It's also very difficult. How can it be made more efficient? And basically, how could this large overhead of flooding be reduced? One approach, so this is basically the second point of search mechanisms that was on the list, is the expanding ring. And there the idea is that you start first with a small time to live. So your time to live is in the beginning, let's say 3. And again, assuming you have a neighbor count, an average of 10, then you have only 1000 nodes contacted, basically. So 10 to the power of 3. And if you don't find it in this set, then you expand your time to live. So you choose time to live of 5 or 7, and or first of 5, and then you contact them all, and you see whether you had success or not. And if you still didn't have success, then you increase it again, and you increase the number of nodes queried, also exponentially. Small problem is with this is of course that you contact already nodes that have been contacted before. So it's bad on one side, but just as a comparison, so with time to live of 3, you contact at, let's say, 1,000 nodes. Time to live of 5, you contact 100,000. So it's okay to contact that 1,000 that you already contacted before, but you also contact 99,000 new nodes. So it's hard to distinguish which one has been contacted before. Okay, why does it work? So what's the point? And the point is said in this little word, the Zipf law of popularity. So if you're not very familiar with peer-to-peer, probably you've never heard of it, the Zipf law. The Zipf law popularity is a distribution, basically, that occurs, that's according to this rule. So just assume you have 1,000 elements, n, 1,000. And let's say that we have a rank. So every element has a specific rank, how regularly it occurs. So one element, I, for example, that's a variable, is the 623rd most frequent one to occur. That you also have in words, so in language, so I think the is the most word used in English. You have it with letters, so E is the first one, the most one to use. And the same you might also have with files or websites that are accessed. So just think of 1,000 elements and they are somehow sorted by their popularity. And yes, then you have another variable S that is characterizing this distribution. And how this all comes to play is with this frequency. So this is giving this formula. I just show you all because the animation is broken. So this formula in the middle is giving you the frequency of an element k to occur. So there you have k, its rank, you have n, and you have s, which is somehow tuning it. And it basically gives out of all nodes that might occur, how high is the probability that mine is occurring. To give you an example, with n equals 10,000 and s is 0.64, then the probability that the next element will be x, which is between 1 and 10,000, is basically that you take the rank of that element, put it under this in this formula, and this graph is basically the result. So if you have if this is the rank of the objects, so you have to see that this is a logarithmical graph, so both on the x-axis and the y-axis. So the first element with the rank number 1 has the popularity to occur of 1%. The second one has the popularity to occur of 0.5%. So so it's always multiplied by not 0.5% but 0.6%. So every rank is multiplied with that. Every popularity is multiplied with that exponential. Do you see the point? Okay. So the main thing that you should take from the Zipf distribution is that you can define for a large range of elements a popularity which is basically according to the logarithmical scale. So the variable s is only tuning how much it is, how the slope is. But in general, it can be said something like the first element is occurring twice as much, so double the time, as the second element. And the third is also occurring only half as much as the second ranked. So just think of this logarithmical scale. It's basically just saying the first 10 elements are having most of the probability to occur, and the last one, the very long tail, is quite rarely appearing, but it's still probable. Okay, so coming back to why is it relevant for this expanding ring? It's telling that most probably you're looking for something popular, because that's of high probability. And it's also probable that somebody else has been interested in that popular thing. So if you start with a small time to live of 3 and you contact 1000 nodes, then with high probability you are looking for something that also somebody else was looking for, and that's probably in this set of 1000 nodes. Only in the cases when you are looking for something unpopular, which is very rare because it's less probable, then you are generating more traffic by extending your time to live and the ring that you are looking in. So this is the main principle how the expanding ring is optimizing the search in unstructured P2P overlays. Another approach is trying to eliminate this flooding idea. So the main point is coming to random walks is that you just send out randomly a query, your query to a randomly selected neighbor. So that means instead of contacting your whole neighbor set in one round, basically with one hop, you only contact one. And he's also propagating it further and further. So you see, instead of having this exponential number of nodes contacted, somehow it's still linear. So there's a lot of luck whether you find an object you are looking for or not. However, in contrast to the previous approach, you don't generate exponential load of messages, but you also don't reach so many nodes. So how can it be improved? So the one aspect is that instead of sending only just one random walk and generating only, let's say, if your random walk has time to live of 10, then you generate in total in the network 10 messages. But if you send multiple random walks, let's say 2 or 3, then you generate 2 or 3 times a time to live. So 2 or 3 times 10. So that means 20 or 30. So you increase the number of nodes contacted, and you also come further from you away, basically, but you still generate only a linear load. And again, you have this time to live, and everybody's checking before retransmission. So the same principle, but instead of exponential number of nodes and exponential number of peers contacted, you only have it linearly. But thinking of the drawbacks of this unstructured P2P overlay is, again, with less peers contacted, the probability that you don't find the objects that you're looking for is also decreasing. Okay, so the same example that we had before. Now a random walk with n equals 2, so we are sending every incoming message twice out, so that we take control on it. And oops, it was too fast. Great. That took me also some time at that time. Okay, so now what we have now by limiting the number of messages, of course we have less messages. In this example, it's 30 messages sent out. And however, our destination in this case, our hop count until we reach the destination, in this case was 6 hops. No, it was 8. It should be 8, I think. Or 7. 7. It should be 7. So the number of messages was reduced, but also it got more improbable that we find our object, and if we find our object, then it takes us longer. So that's a trade-off. The fourth mechanism I want to present for unstructured P2P overlays is how you can find objects with a pure concept basically, so we're still in the area where all the nodes have the equal rights and doing the same, is the rendezvous point. So that you can think of with this graph. And in this case, we have a storing node. So this green node is having some objects. But in contrast to previous, so to that what we looked at before, is that he doesn't keep the information for himself, but he's spreading the information to a subset of other nodes, telling, hello, I have this specific file, please store that information about that I have the specific file on you. So he's contacting these nodes and tell them to store the content. So you can do basically two things. Either you tell them store the contact directly, or you tell them please note the information that I've stored it. So it's the same basically. So that's at the end it's basically very similar from storage. And the requesting node, that's the violet one, he's on the left side. He doesn't send out a flooding, or he doesn't follow the random walk, but he contacts also a specific subset of nodes and asks them whether they have information about this specific content. So, and the black nodes, there's a match. So both the information about the content has been stored, but also the request reached these nodes. And this is basically the concept of a rendezvous. Okay, so having seen basically these four types of search principles, how it can be done, we are now looking at specific protocols, how they implemented these principles. And yes?
In cases of flooding,
yes?
receives a message, the same message from multiple neighbors. So it would discard all the messages except the one, right?
Yes. Yeah.
The message to B and B already has the message.
Yes, so if the protocol, that's why we are now looking soon at explicit protocols, also stores the message ID, which is the same for the whole flood for a specific query, then he doesn't retransmit it a second time. Okay, so now we go into explicit protocols that are implementing these principles. And the first and very, very important, very famous one is Gnutella 0.4, because it was the first decentralized P2P overlay. And it was developed by Nullsoft. They also made Winamp. That was very popular at that time. And Nullsoft was then bought by AOL, which was a large internet service provider at that time. And somehow the source code and the binaries got leaked and were somehow put online. And some people say that it's very beneficial for AOL to put some peer-to-peer software online, because then people want to have bandwidth to share lots of files, and so they have the benefit, and they want to buy better internet connections, probably from AOL. But that's just a rumor. So however, that was somehow created by Nullsoft and published then. Some weeks later put offline again, so the web server where it was available, but it was already publicly available. And there are two versions, basically 0.4 and 0.6. And the one is having homogeneous roles where all the nodes are equal, and the second one, 0.6, they introduce some heterogeneous roles. Also they could use some servers for that. That we will see. So first starting with 0.4. And some basic characteristics of the version 0.4 is that flooding was the main concept, how to find, for node discovery and to search for specific files. And that's exactly how we used it, how we learned it before. So very simple. Okay, and what was introduced? So in addition to flooding, so the same question: what happens if a flooding message was received twice. So there were message IDs that signalized that so that they could learn, okay, I forwarded this message already, so I don't have to do it again. And the hop limit was 7 in the beginning. Okay, so what kind of phases did it have? So how many messages? How did it work? So there were 5 essential messages. Not essential, but in total 5 messages, beginning with ping and pong. Ping and pong means only ping is asking for new hosts in the network, and basically if you send a ping message to one node, then it gives you some information about itself, and the pong is the answer to it. So very simple. With the ping and pong messages, basically you keep the network connected, as you can ask all your neighbors whether you are online, and he answers yes I am. And if you need some new information on some new contact address, then you can also use it for. Then you have the query messages and query hit. The query messages where you define what you are looking for and you flood it. And the query hit messages, they are a response to the query and contain a list of matching files for the peer and a list of the peers and the ID of and the contact information of the peer who has these files. We will see an example how this works. I forgot the 6th message. Yeah, the most then with the query hit you had the information which peer is storing the data that you are looking for. Then you could transfer the files with HTTP. That was the protocol that was used to transfer the files. And the 5th message for the protocol, basically, if you had some troubles in contacting the peer from which you wanted to download it, then you could send him a push message telling him basically to contact you, because you are probably better contactable than he was. You will see why. So how is this done? So the question again is, how do you connect to a Gnutella network if you don't know any peers in before? That's very hard to do. So you have to know somebody, at least one member of the node. Therefore you had the caches, or they were displayed on the website. But typically, if you have a cache with 100 or 200 nodes that you were previously knowing by messages passing on, then it's very probable that one of these nodes is still online. Okay, so that was the point, either web or telephone or the caches. And what they do then, so the new peer contacts that single peer that he has, and he is, so the first picture on the left, so there the ping message is sent out to the previously known host. Picture number 2 shows that peer is sending a pong message, okay, I'm alive, and he is also forwarding only for one hop ping messages. And these nodes also send a pong back to the new peer, and new connections are established. What is special about what you should take care of is that the pong messages are not directly sent to the new peer, so they are reusing the connection that is already existing. That is somehow very often used in Gnutella. Only once that connections are established, they can be used. So you do not want, or it's rarely done, that these connections are assumed that they can be established. So it might be that this connection doesn't work out, so then you don't use it, but you try to contact other nodes. Okay, so that's how a new peer creates his topology, and that he continues to contact. So he might now ask that peer with a ping message to increase his neighborhood and the number of contacts he has until a specific number, probably 30 nodes or 20. Okay. The searching. So in this part, the node again sends out a query message and the query message is flooded with this time to live like we saw it before. Now, when a peer is having a valid hit, then he adds the IP address of the sender, so who he is, and which files are matching the criteria. So it might be if you're looking for, again, Britney Spears, or nowadays probably Lady Gaga, I don't know, then you might have various files matching to that criteria. And these two information are sent over the way that the query went. The messages are sent back to the receiver, to the query sender. So in the case, for example, that the time to live was 7, and the query was walking along, then the query hit is walking the same way back to the requester. And the point is that you do not want to try whether you can contact him directly, because he might be behind the net. So that means, because it's assumed that he has a private PC, you cannot, if you send him a message, then you probably only have his public IP address and his NAT, so network address translation, firewall at home, do not know to which device behind the NAT in the private environment he should forward the message to. So it's typically dropped. So if you have a NAT at home, so if you're a private person and you have one public IP address and several private IP addresses at home, so several private devices at home, then you have this problem. And in order to not basically to do not, Gnutella wanted to avoid contacting that kind of nodes, so Gnutella reused the links that are established, because them you can reuse safely. So if the nodes already have a TCP connection, then they can transfer everything between each other. That's not blocked. So that was the query hit, using the way back that the query took. Okay, so now we know that there was a peer 7 hops away. We have his IP address, we have the list of files that we want to download from him. Now the peer that was requesting and looking for that files tries to set up a HTTP connection, telling, give me that file. So this HTTP GET protocol that's quite old, so more than 10 years before it was published. So nothing new, but it was something that was working quite well. So now we might again have the NAT problem that the peer who offers the file is behind the net and cannot be contacted, only by his close neighbors. So in this case, when the peer is behind a firewall or a NAT gateway, then the downloading peer cannot initiate the TCP connection. So he sends a push message using, again, this path of the query hit to initiate, using this path of the query hit, again, to the peer who has the files and telling him, please send me the file and contact me, assuming that the requesting peer is not behind the NAT firewall and can be contacted. So in this case, the peer who has the file can contact him and send him the file. Still, there's a problem if both peers are behind firewalls and they cannot contact each other. There, it's getting tricky, and it's not discussed here. Later on, we will see it in, I think, 5 or 6 lectures, how this can be done, what kind of net hole punching protocols they are in order to, for 2 peers behind nets, they can contact each other. But this is in general a problem. Okay, so what kind of problems were there? And was it good? So just to summarize, in the first year, until it was not so popular, it was good. But then as it grew, it became a problem. So just to have an example, if you have a time to live of 4 for the ping messages, then you might contact with one single message roughly 8,000 nodes. With one single message that you send out. And the time to live in original Gnutella was 7. So just that gives you an impression how many nodes you contact with one single message, basically. And yeah, so that's a summary. It has a scalability issue, too many messages, and there was a measurement study by Portman and some other scientists, researchers. They had a look on how many, what is the traffic production and traffic overhead for various message types. And they found out that basically this ping and pong for keeping the network connected was very large. And overall also the queries were generating a lot of load. And at the end of Gnutella, so up to August 2000, the most of the peers were just handling ping and pong messages and queries and didn't have any bandwidth for up and downloads. So it was somehow funny because the big goal to eliminate the centralized component led to this fully decentralized solution, which at the end didn't work. So it all the bandwidth was used up for the maintenance of it. So it broke down and lost many users, and it was for some weeks unknown what happened, but they found out that basically it's all crashed because it wasn't scalable, although it's peer-to-peer. So peer-to-peer is not from per se and naturally scalable, so you still have to make sure that you are not generating exponential amounts of traffic and message overhead through one single message. So what did they do? So how can these scalability issues be tackled? So one approach was, okay, you could of course optimize the number of hops and trying to tune that parameter, but that's still, you are still generating exponential many messages. Then what they also wanted to do is to optimize the ping and pong messages so that you do not send out messages and wasting traffic, but you somehow collect some information in advance, which peers you should contact and how far you should forward that message. Also, this was not used finally. Okay, then you could say, yeah, just drop all the bad nodes and move the low bandwidth users to the edge of Gnutella. So you have basically a core of Gnutella network, and the weak peers are only using it as a client. So to start their queries, and the Gnutella network resolves the query, and at the end they receive a result. Okay. And the idea was then, okay, let's call the core of Gnutella ultra peers. That was somehow introduced then in Casa. That's basically the next step of Gnutella, what we are going to. So ultra peers, super peers, the main concept is that you have very strong peers which should do somehow more than the other ones. What can be also done is to use file hashes so that it's easier to also introduce some caching, basically. Instead of storing too much metadata on every file, you just have one single identifier that you can reuse, and you might have some caching of knowledge where content is. But finally, what has been implemented and led to Gnutella 0.6, and it's still the final state. There's no new Gnutella, and I'm also not sure how popular it is, but the concept is still very important. So they introduced super peers, and that means they introduced two roles, basically, the normal peers and the super peers. And for both of them, they have a dedicated network on how to resolve the queries. Okay, but these Gnutella 0.6 we won't see here, because we are in this part of the lecture, we are still talking about the homogeneous networks. It will be, I think, in 20 more slides, probably next week. So just keep it in mind that the super peers will somehow solve some problems that Gnutella 0.6 had. Okay, coming back to the what kind of further problems there were, which should also be tackled, and we will see whether Gnutella 0.6 tackled these. One big issue was free riders, and free riders is the synonym for selfish users who are not willing to contribute bandwidth or to share files. They just want to download and don't want to contribute anything. That was at that time the type of user I was, and the idea was that you just download, of course, that time only Linux distributions that were free in the file sharing networks, so only legal stuff, and you didn't offer any other files. You throttled the bandwidth that you were giving to the upload bandwidth that you were giving to the application. And there was some study in 2000 which said 70% of the Gnutella users share no files and 90% answer no queries. So even the 30% that share something do somehow not answer to the queries. And that was really a big issue because most of the load was then still at the back of only 10% of the nodes. Some solutions how to take care of this problem that were proposed were to give some incentives, so to make it somehow better for the users if they share. So one idea was to only accept connections, to only upload to peers. No, to only, So to only give to peers who are also giving to somebody else or to you. So only accept connections to peers that are sharing. But how to find it out? And even if they are uploading, do you know what are they uploading? Are they uploading some fake files, or are they really uploading some useful files? There were also some approaches of micropayment, basically saying for every little bit that I upload, I get a nano currency. It was called Mojo Nation. The Mojos were the virtual currency like Bitcoin probably nowadays. And the idea was that people who are sharing a lot should get some micro money for it. And with this micro money, they can also buy or download from other users. At the end, this micropayment didn't work out because basically it was too complex. And there came also another solution that were solving the incentive problems, that was more efficient, and that also didn't overload the nodes. And that other solution that came basically 2005, and that was BitTorrent. But later on we will see more for that. Okay, the last aspect for these homogeneous peer-to-peer overlays, how this can be done, is following the rendezvous idea. Like it was said, we have a region, so these are only subsets of the network, so the network is larger, and you have a data bubble where you basically announce what you have. You might also store your data there, and you have a query bubble that's also contacting a subset of the network. And if you are lucky, and the protocol makes you lucky, you have a rendezvous point where the announcement and the queries are matching. So in this case, your query is successfully resolved, and you are either getting the file or you're getting the information where you can get it. And the point is that for all of these, so what is the new part about it? So the new point is that previously we didn't have any announcement what kind of data we have. So the announcement costs were 0, so O of 1. And the query bubble previously basically was O of n. In the worst case, we had to contact every node to find what we are looking for. Now we increase both the data bubble cost, so the announcement cost, to O of square n, with n being the number of nodes, and the query bubble is also in this time reduced from O of n to O of square n. And if both of them are O of square n, then you can prove that with a high probability they are matching. So how does this come? So does some of you know why this is so with O of square n? Why we have this matching? Any idea where it comes from? So this comes from the birthday paradox. So the birthday paradox is just saying a year has 365 days, and how many people do you need in average, or at least, in a room, let's say, to have two persons having on the same day birthday? And that is 17, which is, I hope so, the square root of 365. And this is just probabilistic, and that's the birthday paradox. So you need just O of square n, basically square n in the birthday example, users to have a probability higher than 50% that two of them are having on the same day birthday, and the same is also here used. So what else is in this protocol called bubble storm, using the rendezvous based idea? So bubble storm, like Gnutella and the other overlays, use a random topology. So the neighbors are chosen randomly, and that also helps in maintaining the network because you're not really caring where you are and to whom you are connected, so it's just random. What you, however, have to have is you have to calculate the square of n. That's why you need to somehow have the number n, so how many nodes are in the network. So looking at Gnutella, you didn't need to know how many nodes there are in the network. It's you just have your 20 neighbors and that's it. Here you have to know how many, the network size in order to measure and to define your bubble size. But there are also some mechanisms for that. If you look through the lecture slides that are coming, so that will be the point of monitoring. There we will also have a lecture on. And just to give you a short some words on it, so through gossiping, with telling your neighbor how much you assume they are in the network, and some mechanisms, you can quite come close to the real actual size of the network. So they use this topology measurement. What else do they do? The bubble cast, that's basically creating that bubble, both for the query and the announcement. And it's allows to quickly replicate these and to create these bubbles of desired size. And this maintaining the specific number of the specific size of the bubble, because you want to come close to the square n. That's the bubble maintainer. There they have a specific count method, how they count how many nodes are really contacted with their bubble. And let's see how this works in total. So again, the random graph is supported with the birthday paradox. So that's the point that the match is created between the announcements and the queries through the birthday paradox, even if the bubbles are randomly somehow placed and the peers for these bubbles are randomly chosen. And what is also done is, we will see what the benefit is that the bandwidth, it comes also to play. So if a node has more bandwidth, then he also have more neighbors. So that influences the distribution of the bubbles basically, and also makes sure that no peer is overloaded, but every peer is loaded to a specific degree in terms of percentage. So if you have 20 kilobytes per second free, then probably still 40% are loaded. If you have lots of bandwidth, you have a very small bandwidth, still the utilization of the bandwidth is the same. And what's the motivation? So the motivation for bubble storm was basically, in flooding you had the low latency, you really quickly reached all the nodes that you were looking for, and it was reliable, so it worked if the nodes had enough bandwidth. But the problem was, on the one side, okay, if you flood, then you really cannot create that bubble sizes that you want, and some nodes are stronger loaded than others if the neighbor count is the same. With the random walk, you could somehow balance the link load. There you could make sure that stronger peers have also more to do, and you could also control how far you get, but it was unreliable, and you didn't have the results in a short time. So they took basically so as you can see, the presentation is from the persons who also created Bubblestorm, so it's very motivating for it. So according to them, they took the best of both worlds. So they took from the flooding basically not a hop counter, but a node counter. So they count how many nodes they reach. And they also had a fixed branch factor. So they didn't send it to all neighbors, but to only limited size. And from random walk, they took the idea. So in this picture, it's not well visible, but if you would have had a multiple random walk where in every step you split up the message in two or send it to 2 or 3 neighbors, then you have a limited branch in every step. So in together, it should all work out very well. At the end, we will see what still performance lags it has. Okay, so the bubblecast, how does it work? So the bubblecast, that's basically creating the bubble both for the announcement, telling which documents you have, and also for the query, announcing what you would like to have. So you have so first of all, you have to find out the network size. Let's assume that you have from somewhere, from some other mechanism. Then you count the square root of it, or a little bit modified. In this case, it would be 17, for example. Now what we want to do now is we defined the number of replicas, that means the size of the bubble to create, and it is sent out to the neighbors. Basically, I, as a first node, are already decreasing the number, so I'm taking a replica and I send it out to my neighbors and split it in half. So the one neighbor should create a bubble of size 8 and the other one as well. So the counter is always split between 2 neighbors. Okay, so let's continue. So there's a replica and also split the counter. So now my 2 neighbors are contacting also each individually 2 neighbors, and so it's continuing. Very simple procedure, but at the end what I had is that I created a bubble with 17 replicas of my announcement or query. And what has also been done is that the routing depth, that means how far the message went, is only differing by at most 1 hop. And that's a good thing, because the longest route to my node is at most logarithmic basically to the bubble size. So in this case, my bubble size was 17, and this is a 3, and with a split of 2 at every step, I have a logarithm. So the depth of the tree is logarithmic to the base 2. So if a result is available, I'm quickly informed, and there are not long paths to my node. Okay, and so how does it then work out? In this picture you have just assume the peers, and all of them are able to store data in query, and because the network topology is random, also my bubbles are random, and both my data and my query are randomly stored. And if I have some matching, then I'm happy, because that peer can answer me that he has some fitting data. Okay, so what little modification is there first also to see. What they also did is that faster peers who have higher stronger peers with a higher bandwidth have also more neighbors. That means they have more links, and that means that the probability that they are reached is also higher than for peers which have lower bandwidth and less neighbors. So that means even if we support this heterogeneity and support that peers might have a different node degree, then it even gets better, because stronger peers are much more probable to store queries and data in one place, because they are reached more frequently. So this is a good thing. Okay. So what is the property of these kind of bubblecasts? So as we have seen, this bubblecast is only making sure that you contact number of nodes that you specify the number in advance, and you can contact these specific number of nodes and either store announcements on them or queries. What is further there is that this fixed branch factor. So in every step by creating the bubblecast, it's only the branching factor, which was in this case 2, is fixed, and that's supporting the random walk. So that's supporting the load balancing. So no peers are overloaded in too high degree. What is further done here? By counting the edges and the nodes, you can really precisely control the replica count. So you're not anymore counting the hops like previously, but really how many nodes you are contacting. So that's a good thing. And with the logarithmical routing depth, you make sure that if you find a match, then you are quickly informed about it. And so in the worst case, in the random walk, there would be a linear traversion of the path back to you. In this case, it's only logarithmic. Okay. Even if there's message loss, that's not a big deal, because you only lose one small branch of your tree, so of logarithmical size, if one replication message is lost. And also, it's very simple to maintain due to the randomness. So only good things. And what they also say is that with the bubble storm, you really have guaranteed traffic overhead for your operations, which is a constant times square root of n per operation. And with that, with this C, you can really tune your quality of your network. If you, for example, choose a C equals 4, and you have 4 times the square root of n bandwidth consumption per operation, then you have still a probability to find what you're looking for with 5 nines. So very good, reliable operation, which is before in Gnutella quite unreliable. Yeah, the full equation, so what really determines the quality of the costs generated in Bubblestorm are first also introducing the peer capacities, so how much degree and freedom you give there, how well your sampling is, that means how well you can count the network size. It also introduces some variance between query traffic and post, so announcement traffic, and you can look it up. So just some words on the drawback on Bubblestorm. It's all very nice, but you can still think of whether a constant times the square root of n is acceptable. So if you want to have a very good reliability, then you would choose probably 3 as a constant, and the square root of n is still a large number. So that's still something that might bring you some issue. Another point is, just assume that you want to update the information that you once announced. So you stored some information out there, and now you want to change it. So probably if you would use Bubblestorm for a social network and you wanted to store your profile information, then you published it, you are happy that it's replicated, people can access it, but now you want to change the information. Then you do not create the same bubble in the network, and that means that you have as well your old information as well as the new information overlappingly in the network. So you cannot really access every replica that you once stored in the network and change it, for example, or delete it if it's very privacy concerned. Okay, so this was the last slide for the homogeneous peer-to-peer overlays. So in the next lecture we will start with the heterogeneous peer-to-peer overlays, where we will see basically that some new roles are introduced, where we have two types of peers, and we will see what kind of benefits this brings. But for today, I thank you very much for your attention. Thank you.